All right, let's start today. Last time we looked at classes, right? So we did a complete overview of classes last time. And there's two topics left, vectors and application development. What we could do is jump into vectors because it's related to classes and will help us think about classes a little bit more. The other thing we could do is to kind of do some review for today's quiz. And look at some topics or look at problems that you're having with the assignments. Yeah.
I just have a question. I was wondering how you could use or how would you implement the sorting and searching function in the same plot, because you can only use the binary search if the number's already in order. So how would you use the sort for the search function? Would you call the sort instead of the search?
Well, no. So sorting and searching are two different tasks, right? So they're two different things. But they're related in the following way: that if you sort first, then you can use binary search. So that's the only connection. So if you want to sort first and then use binary search, you can do that. It's faster to do linear search. If you don't need the elements sorted, don't sort them first, because sorting is, let me see if I can explain it here. And to sort, if I have, n elements, sorting, according to our routine, sorting takes n times n. The amount of time it takes to sort a list is, using our routine, is n times, is some constant times n squared. But searching, linear search, is just some multiple of n. I mean, it's a different c, right? But this tends not to be important. When n gets large, the c doesn't matter anymore. So searching, here sorting is going to blow up, n times n, that's n squared, whereas searching is just, if it takes 1 millisecond to look at one element, then if there's a million elements, and it'll take a million milliseconds to look at each one, roughly. Now, this is our sorting, but the better sorting takes some constant times n times log n. I'll do it like that. So that's faster. That's faster than n squared, but still it's not as fast as linear search. So you wouldn't want to sort just to use, binary search, because binary search, of course, binary search is takes some constant multiple of log n. So that's how fast binary search runs. This is very fast. So you can go from linear time to log time, which is a huge improvement. But to sacrifice, up front, n log n cost doesn't justify. It's not justified. It's too much of a penalty. On the other hand, if you're going to do a lot of searches, then you just sort once up front, and then for the next, million searches, they're going to run fast. So it depends on your situation, what you need to, what your application is.
Okay, so
That's
you wouldn't wanna
probably
do-
that's probably fuzzy, but that's my answer. Yeah.
No, yeah, I got you. It's just so you wouldn't wanna do a linear search unless you have to sort them, basically.
So if you don't sort, you have to do a linear search. If you sort first, then you can do a binary search. But when you build a list, think about it. If you build a list just by putting random elements one after another, then you got to use linear search. But you could also, when you build your list, you could build it in a way that every time you add a new element, you maintain its order. You either keep it always ascending or always descending. And then as you build your list or modify your list, if you maintain the order of the elements, then you can use binary search. So to get a list of sorted elements doesn't mean you have to sort them, but it means you have to maintain the list so that it keeps its sorted order. And I think there might be a problem in the assignments to do with that. Is it in here? Maybe it's in vectors. It's probably in vectors. Look at this. That's why today is good. Vector insertion. This problem is what we're talking about right now. So suppose a vector v. Now, a vector is just an array. It's an array, okay? It's not hard to understand what a vector is, just a list of values. So suppose a vector v contains a sequence of integers ordered from lowest to highest, so it's ascending. For example, v might contain the values 3, 6, 7, and 12. So it's already sorted. Write a function called insert that takes this vector v as a first argument and an integer k as the second argument. The function inserts k into the vector so that it preserves the order of the element. So that's what I'm talking about. You can have, as you're working with this list of values, you can, every time you modify the list, you can preserve the order of the elements. Here's an example. Let's suppose that v was 3, 6, 7, and 12, and that k is 5. After calling the insert function, v would be 3, 5, 6, 7, and 12. In other words, we'd put the 5 in the right place to keep it sorted. So now, one of the benefits of keeping things sorted is that the lookup time is very fast. It's log n lookup time. So that would be one reason to keep the list sorted, because a search is very fast. So in your implementation of insert, do not use the insert function of the vector class. Although we could use that. This doesn't even matter. That we could use this. Maybe I don't need to say that, but you don't need to use insert there. So how would you do this problem? How would you implement insert? Let's take a look at that. So we want an insert function. It takes a vector of integers, v. See that? That's a vector of integers, v. Actually, it needs to be a reference. We talked about this before. I'll explain why we need this. This is important. And we want to insert a value k. And let's just do nothing. So we have a vector v. By the way, this is how you declare a vector. You use the angle brackets. But you know, we can have a vector of double. You can have a vector of point. You know the point class we defined last time? You can have a vector of int. You know? You got to put a space in there, by the way. You can have a vector of anything, any data type. We're going to do vector of int. So a vector of int v, so that's an empty vector, it has 0 elements in it. Now, unlike an array, the main difference between a vector and an array, well, a big difference between vector and array, is that the array, after you declare the array, it's given a size when it's declared. And the size never changes. But a vector has a flexible size. It starts with, here we're creating a vector with no elements. It has size 0. And then to add an element, we use the dot notation. We call a function called pushback. Let's push back 3 onto v. Right, let's do this here. Let's use this as our test case. 3, 6, 7, and 12. So we create an empty vector v, and we push onto it a 3, then a 6, then a 7, then a 12. So the vector at this point will look like this: 3, 6, 7, and 12. That's the vector. It looks just like an array, but it's a flexible array. We can change its size. And it has operations that are accessed through the dot operator, such as pushback. In this class, you only need to know 2 operations. You need to know pushback, and the other operation you need to know is size. Pushback modifies the vector by adding another element to the end of the vector. It's a size function, returns the number of elements in the vector. So we can do v.size. That'll print how big v is. Look, if we come up here, if we print the size of v here, it should print 0. And here, it should print 4, because we pushed 4 values onto v. Let's check that. Oh, v, there's a compilation error. Can someone help me out? This is the beginning of the error, right there. Variable or field insert declared void. And then it's got this little symbol here pointing at vector. It says error. Who can fix this problem? What do you think that problem is? Try to guess at the problem. Vector was not declared in this scope. The compiler is saying, vector? What's a vector? Don't you remember it used to tell us that about assert? Assert? What's assert? You got to include the vector header. It's a part of what's called the standard library, or the template library. Yeah, it's a standard library. It's the built-in library of functions. See, the language, the core of the language doesn't have a vector in it. It's sort of added to it and then provided with every, because you can implement the vector class yourself. And but you know the language specification says, well, it's such a common data structure that let's go ahead and require all compilers to have this built into their system. So when you install the compiler, and there is a vector header, and you can use it, you can include it in order to get access to this, to the vector functionality. All right, let's see now. So it's here's the 0, there's the 4. So v dot size and pushback. Those are the two functions that you need to know. Now you see v vector is actually a class. You know what we were doing last time? We did like a point p. Remember that? We have the data type followed by the variable name. So now we have a point. We'll call it p1. And then we have another point. Call it p2. So we're creating instances of the point class. Here, we're creating an instance of the vector class. But this class is a little different than the class that the point class that we looked at last time. This vector class is a parametrized class. It's a template class. They say template class. It's defined as a template. So this is a vector of int class. But you can have a vector of double class. You can have a vector of some type in here. And so this vector is called a template class because it's a template that you can use to create other classes. And the class that we're creating is the class which is a vector of int. Let's call it a template because we did not define a template class, but we could have. We could have said a point in 2 dimensions, and this is a 3-dimensional point. Or passing in a parameter so that the source code. Actually, what happens with the template class? You can open up the header, the vector header. You can see in there it's just a bunch of source code. The compiler takes the source code and it replaces. In the header is defined as a vector of t. See, and then it'll have a bunch of t's in the source code, and it'll go through that and replace all the t's with int, and then compile the resulting source code. So these template classes are just a source code which has some replaceable parameters in it. We're not going to look at how to define them, more than what we've just mentioned just at this moment. That's for a later class. So we have a vector of int here. And now what we want to do is we want to call insert. We want to call our insert function. And we want to insert, what was it? Insert 5. We want to insert 5. So k is going to take on 5 here, see? I'm going to get a 5 in there. So after we call insert 5, we want the v to look like this. Let's go ahead and assert. So v of 0 needs to be a 3. V of 1 should be a 5. And v of 2 should be 6, 7, and 12. So this is our test code. We're going to write the function, the test code first. Now this should fail. Let's see the test fail. V of 1 does not equal 5. See, actually, this one passes because, the function does nothing, so we're passing in this vector. By the way, this would also fail because there's no index 4 in the vector. The vector has only 4 elements, so it only goes up to 3. So maybe we should have an assertion to check the size. Check that v dot size is 5. So the size is 4 coming in, and then into the insert function, and it becomes 5 when we finish. So that's where our assertion should fail at that point on line 21. There it is, line 21. The size didn't change, and let's make that. Let's fix that one. So when v comes in here, we do v dot pushback. We're going to push back k. All right. We'll put k at the end of the vector. Now, after calling insert, the size will be 5, and we'll pass through there. And because now what we're doing now is we're doing this. We're appending the 5 onto the end of the vector. Okay, that's what we're doing. It's just partial solution here. We're just doing a step at a time and analyzing this at each step. So we call pushback k here. They're putting the k on the back of the vector. So now this assertion on line 21 should pass. And this assertion on 22 is also good. That will pass. But the assertion on line 23, as before, we don't get a 5 in that position, so that will fail. Let's just see if we have everything under control and that works the way we want it to. Yeah, there it is, line 23. Line 23. The assertion v1 of 5 has failed. v1 is 5. So we've got the right size, we just don't have things in the right order. So this is what we'll do. We'll start here, and we're going to swap with the previous element. See that? Swap with. We're going to keep our index. We're going to keep our sort of eyes on this 5, and we're going to look at the value before the 5. And if the 5 is smaller than the value before it, we're going to swap with the value before it. So here we're going to swap 4 and 5 and 7. See that? Now we're going to compare the 5 with the 6. Got to swap again. Now they're in the right order. We compare 5 with 3. Everything's good. We'll stop right there. So we can have a loop. After adding the value, we can compare. No, we're not going to do it like we won't use a while loop. For integer I equals, now I will equal the position of where k is put. So v dot size minus 1. There it is. So there's our loop. We're going to start with I. It'll look like this. Let me show you this. It'll start with, we push back k, and we're using the example 5. So we start with I pointing to the 5 right there. See, that's why, because we know that k is on the end of the vector. So the last index is size minus 1. So I will equal 4. And the index 5 is in position 4. So we'll start with there. And in the loop, we're going to decrement I. So we're going to start at the end and we've got to go to the left. So I has to get smaller. And then we have a condition. This I'm not sure about yet, right? I got to think about that. I don't know if that's the right condition. Because remember, there's always an off by 1 that we have to worry about. But we start like in golf. We just want to get the ball on the green. Right? We're not going to go for a hole in one. Unless you're really smart, then you can just know, oh, I know what it is. But I'm just going to get close to the solution. I'm just going to say I greater than, maybe it should be I greater than or equal to 0. Maybe it should be I greater than 1. I don't know what yet. I got to think about it. Could be off by 1. But I know that I has to slide left. It's got to go lower, and it can't go into the negatives because there's no, an index, the indices cannot be negative. So any index that we use in the program can't be smaller than 0. We can use a 0, but we can't get smaller than a 0. So we need to do the comparison. So if v of I, that's the number we're looking at, if v of I is less than the one before it, then swap. Well, the one before it is v of I minus 1. So if this is the case, then we want to swap v of I with v of I minus 1. And what is going on there? Maybe I'll make it easier to look at and do it like this. How's that? So if v of I is less than v of I minus 1, the v of I, the k that we inserted, is smaller than the value before it, we're going to have to move k to the left by 1. Oh, sorry, that's not a brace. It should be a bracket. I think that's going to do it for us. It looks good, but there's a problem. What happens when the value, there's some special cases here I want to be concerned with. Let's call insert with the number 2. So we want the value to be it needs to come all the way up to the front, right? Actually, let's make it minus 1. That's scarier even there, okay? We're going to try to break our code. So now we're going to do these assertions. See, because maybe we're off by 1. I'm worried that I is going to go to the left and slide too far to the left, or not go far enough to the left. So I'm going to have some test code in there. I'm resisting the urge to reason about it first. I want to write the test code first. This is a discipline called test-driven development. After we write the test code, then we can reason about whether we got the algorithm right, and then our test code is all set up to test it. I got to tell you, that is a style of programming, test-driven development. And it's an optional style. I don't always use it, I got to tell you that. When I teach the class, I teach it, but I don't always adhere to this style of development. To be honest with you, I don't usually write test code first. Let's see. So the size should be 6, and then these values are going to change. 12 is going to come to here. 7 is going to go to there. 6 will go to here. 5 goes to there. 3 goes to there. And minus 1 gets into here. I'm pretty sure this is going to work. Oh my God. The test code is bad. Look at that. Test code is bad. All right. See, we were not off by 1. We could have some more tests as well. Like, what happens if we push? What happens if k is 100? You know, does it work when it's on the very end of the vector? I think it does. You know, I mean, I think a lot of programmers would not bother to write test code for this, but we're doing it as an exercise. See, this condition here, if we made that greater than or equal to 0, let's suppose that's what we thought it was. See, I know that's a problem because if we let I hit 0, then we're going to produce an index of minus 1 here. So we're going to compare v of 0 with v of minus 1. V of minus 1 is not a legitimate index. And the test code might fail and it might pass. It fails. Look at that. So the code doesn't crash. It doesn't say, oh, index out of bounds. It just computes, you know, v of minus 1. What's v of minus 1? It's the 4 bytes preceding the beginning of the array. The array, just like, vector. The vector, just like the array, the values are guaranteed to be represented in memory as using a contiguous memory. So the elements are contiguous. They're touching each other. And the language allows a negative index. So we can start looking at values that are before the beginning of the block of memory that the vector is stored in. And we don't find a minus 1 there. That's what it's saying. You know, this test failed because we swapped, because what happened was we probably found a 0 there, okay? Well, maybe we found, whatever we found, minus 1 was less than the number. So we swapped it. So we wrote a negative 1 into memory that we shouldn't have touched. And we swapped a new value up into v of 0. So actually it corrupted the memory. That's why this language is problematic when it comes to security. Now this is called you would call it a form of buffer overflow. The code is actually modifying memory that it wasn't intended to be modified. So it's, you know, hackers can sort of use that to their advantage and insert something, you know, into memory that shouldn't be there, that kind of opens up some kind of a hole, an opportunity to break in. So that's one of the weaknesses of this language. In other languages, we'd have a runtime exception. It would say, you know, index out of bounds, you know, you can't, they wouldn't let us do that right there. They say, you can't look up v of minus 1, and then would throw an exception, and the program would terminate with a little error message. So that would keep us from that buffer overflow issue that you get in this language. So anyway, this can be corrected here. And that is, that's an introduction to vectors, and it's also the solution to this problem number 7, which may appear on a quiz. And it is also lets us understand a little bit about searching and sorting a bit too. It's sort of tied in with that. Because this is the kind of insertion algorithm you'd want to use if you wanted to maintain a big list of values that you frequently search through. So you want to use binary search to look through it to get things quickly. So this is how you would need to insert values into that. Although I got to tell you, this is an expensive way to insert, because every time you insert a value, you've got to move lots of numbers around. So there's data structures that provide a faster way to insert values in a list. But then you can't use binary search with those either. So anyway, that's for another class. I don't want to get into that. Let's take a look at this vectors. Here's another way. You can create a vector of size 20 or any number using that syntax there. This is the pushback operation. It's the size operation. And popback, that's to remove the last element from the array. So this is some code that shows that. Here's another lecture I did in the past about this. So we're just, it's pretty straightforward. Vectors are pretty simple compared to the classes topic that we covered last time. That's much more complicated. But I wanted to look at another problem in here. Let's see, do I have it in here? There it is. Count prime. Here we have a vector of number, whereas number is a class that we define. Did we do the number class? We did the point class, so we could do points here. So this is, we can have a vector of point. This exercise here, you have a vector of number. So in the classes assignment, there's this number class. You need to implement this number class. Then in the following vector assignment, you have to use the number class here. Here it is. Here's the main. I give you the main code. You create a vector v that contains number instances, not integers anymore, but number instances. And here's 100,000. So this uppercase n is set to 100,000. So I have a loop that runs 100,000 times. And what we do is we generate a random number r. We want to make sure it's not a 0 or a 1. So if we just create this little loop here, like, see that? We do r, we want just r equals rand. But if r comes out as a 0 or a 1, we want to toss it out, okay? So we put this in a do while loop and run it, while r is less than 2. So if we get a 0 or 1, r will be less than 2. So this will never happen. I mean, maybe happen once in a 50 years or something. I don't know what, but you're not going to see, rand is not going to return a 0 or a 1 very often. But just to be perfect, we're going to do this. So what do? Once we get this random number r that's not a 0 or a 1, we're going to pass it into the number constructor. And then we're going to push that number object onto the vector v. So we're going to have 100,000 number instances. All right, so we have 100,000 number instances. Now, the number class has, this is a number, we've got 100,000 number instances. It's got some n in there. That's the integer we passed. That's that r, that random number we passed into the number class. Then it has this is prime function. So if we call the is prime function, it'll tell us whether this number is prime or not. It has the is lucky function as well. So what we're interested in doing is we want to find the percentage of primes that are in the range 2 to n. How many primes are between 2 and n? What's the percentage? So we're just trying to, answer an interesting math question. What's the probability that a random number, which is less than 100,000 is prime? What's the density of prime numbers, in this range? Now, the math people, they have studied this problem inside and out. They've got all kinds of theorems and discoveries that they've made about prime numbers and their distribution. So this is just, this is kind of a mathy problem here. And I'm not doing it, this problem doesn't handle this in the most efficient way. We don't need to create a vector of V. We just can have a loop that, we can just call the is prime function in this loop here. We don't have to store numbers in a vector, right? But I had to create some problem that would show, how you might, how you would use a vector of some class that you defined yourself. So what you need to do is implement count primes. You got a reference to a vector of number, and you call it here. So how many prime numbers are in that vector of 100,000 values? You divide that by 100,000, and it gives you the percentage of primes. Now this is an estimate, it's not exact. We're not passing a vector of 100,000. I say, that's right, the percentage, this is not right, is that? So a rand, no, it's not, this is not correct. Oh my gosh, let's fix that. All right. This is the first time I use this problem. The percentage of primes in, this should be int max. Is int max defined, or is it max int? Is it max int or int max? I do it like this. So it is int max. Okay. It should be, it should look like this. Is that C limits or just limits? Is that C limits? Limits.h. Limits.h. Sorry about that. It was good I fixed it. So it's, between 2 and the largest integer, we just took a sample. We didn't look at every individual integer between 2 and the largest possible integer. We just picked out 100,000 random integers in that range, called that is prime function after creating a number instance, counting the number of times is prime, it returns true, dividing it by the values that we generated gives us that estimated probability of having a prime number in that range. The estimated probability of a number in that range being prime. Okay. Any questions? No. So I know I kind of lost you there, right? But when you work on the problem, you'll figure it out. I don't want to, beat a dead horse here. I know you're kind of lost your focus on that. And it's partly my fault, but when you go to tackle this problem, that's the purpose of the problem is for you to work out the details and to get competent at using classes such as number and also the vector template class. So it's a good problem to work on. Is there anything else you want to look at? I think the best thing for you to do is to just work on this and see how far you get. And if you need help, then talk to me or talk to Mark in the lab. Okay, I'm going to stop here unless there's anything else you want to talk about. So I covered everything I wanted to today. And that would leave one topic left in the course, application development.
When is the first test in the class?
Huh?
When is the first test in the class?
When is the first test?
Yeah, not a quiz, but a test.
There's only a final exam.
Oh.
There's quizzes, there's 8 quizzes, 1 final exam. Final exam is on the day of your lab. It's either August 29 or August 31. Okay, yeah.
Will we be meeting those days for class?
What's that?
On the 29th, which is Monday, today, like a class?
Oh, yeah. Do we have a class on the 29th? That's a good question. Should we?
Yes.
Yeah, we'll have it. I'll show up. I'll be here. But what we can do is, if you have questions, I'll just answer your questions. If you want to do more application development stuff, it's really for application development. That's kind of the goal of what we're working on. I mean, we're doing all these practice problems, but they're kind of meaningless. But really, the meaning comes in when you build useful applications. And although we're not quite at the point where we can, well, I can show you some useful applications that are small that I've built. And then we'll take it from there. We'll see what you want to do. Okay. So yeah, we'll meet on those 2 days. Those 2 days will be to answer questions that you have, maybe about the quiz or the final, to do a review. If you don't want to do that, we can focus on application development topics. So on Wednesday, I'll start talking about application development on this coming Wednesday. And you'll see that final assignment, there's an exercise, unit conversion. It's to convert meters to inches, feet and inches. Exercise 2 is to compute change, right? So if something costs 17 cents and you give the cashier $1, how many quarters, dimes, nickels, and pennies do you produce? You know those little change machines where the money comes out? So we're like, need to do this to program a change machine. So we're programming a change machine here. All right, so how many of these different coins do you provide to when the cost ends in so many cents? So those are 2 exercises. Those are relatively easy to do. Those are required. And then there's 2 extra credit problems. One is to implement tic-tac-toe, so you play the game of tic-tac-toe. And the other one is to do some graphics programming using the SDL2 library. I'll show you that real quick. Simple direct media layer. Well, look, see, Cave Story. Anyone play Cave Story? Yeah, you know it. Yeah. So that was built with SDL, not the original Cave Story. I think. How old is Cave Story? It's really old.
That's like 10 years at least.
Yeah, maybe more. be more than 10 years. But this was the new version, the remake of Cave Story. Cave Story was this old, it was a free Japanese game. I mean, it was only in Japanese, and the programmer released it for free. And it was really old. It was more than 10 years old. And people provided, English translations, and you had to get this free game and then put the. Did you ever have to do that?
Yeah, to patch it so you can play in English.
Yeah. But now they have a version that runs in, I think, Steam. They sell a version of Steam that's easy to install. Anyone know this one? No.
Oh,
XCOM. The guy that, what's his name? Sam Lantiga. He's one of the authors of the main authors of SDL, and he works at Steam right now. He was at Blizzard before that, so he's a visible person in the industry. He's at Valve, not Steam. The company's called Valve, and so there's a lot of little like indie games that have been built with this library. So if you want to take a look at, so what we'll do is in the time that we have, we'll take a look at how you would set up your development environment. Maybe one way to set it up, and start tinkering with that game development library. And then the tic-tac-toe, we can talk about that as well. Anyway, that's for next time. So that's it. Nothing? Okay.